Hello everyone, I hope you all have had a splendid day. In the video we're going to talk about the implicit differentiation, which is the second to last topic in chapter 3, okay? So let's begin by talking about why you would use implicit differentiation, and what better way to start the conversation with an example of implicit differentiation, of course. So the function x to the third plus y to the third minus 9xy equals 0 is defined at every point, which means that it is also differentiable at every point, right? So the function is defined, then it's also differentiable at every point. So upon first sight, this looks like an easy question that you can differentiate, because you're probably thinking to yourself, okay, well, I just move all the y's to one side and I move all the x's, right? And I get myself a pretty nice function in which I can differentiate, right? However, you will soon realize that there is no way or no easy way to isolate the variable y using the mathematics skills that you possess right now, because none of the three terms share a common variable or constant, okay? So what are we going to do at a situation like this? Well, the answer is to treat y as a differentiable function of x and differentiate both sides of the equation with respect to x, right? And in order to do that, you have to use the differentiation rules for sums, products, and quotients, and the chain rule, of course, okay? So, after you do that, you then solve for dy dx in terms of x and y together to obtain a formula that calculates the slope at any point x, y on the graph from the values of x and y, okay? Let's work an example and just make the jumble that I just read a bit more clear. So, we're asked to find dy dx if y squared equals x, right? Now for something like this, you could just move everything to one side and say the absolute value of y is equal to x raised to the 1/2 or root x, okay? But we're not going to do that. For the purpose of this video, we're actually going to use implicit differentiation, okay? Now in order to find dy dx, we simply differentiate both sides of the equation, this equation, okay, with respect to x, treating y as a differentiable function of x and applying the chain rule, okay? So y squared equals x. Well, now we're going to differentiate, okay? So we move the 2 up, right? 2y, dy dx, right? This is the chain rule, because you have to mention that the y is a differentiable function of x, excuse me. And your x just becomes 1, right? Now you can write dx over dx, but there's really no purpose in that, okay? So next, what you're going to do is you're going to find that dy over dx is equal to 1 over 2y. All right, right there. There you go. That is your differentiable. That is your that's your derivative. Okay. Now that wasn't too hard. Let's do a slightly more challenging example to reinforce that idea. Okay. Now, example number 2 from chapter 3.7 from your book asks us to find the slope. So find m. Right. That's your slope of the circle x squared plus y squared equals 25, right? At the point 3, -4. And this is just a circle origin at the center with a radius of 5. So what we're going to do is we're going to help, I'm going to help you find the derivative, okay? Now the circle is not a graph of a single function of x because it does not pass the vertical line test at any point, okay? But it is the union of the graph of two differentiable functions, and they are y1 equals root 25 minus x squared, and y2 negative root 25 minus x squared, okay? Now the point, now point 3, -4 lies on the graph of y2, right, because it's below the x-axis. So it is possible to find the slope by calculating explicitly, and that's by taking the derivative of this, right? And that's by differentiating y2 and evaluating that x equals 3, right? But we can also find the slope much more easily by differentiating both sides of the equation of the circle implicitly with respect to x, okay? And how are we going to do that? Well, we're going to do this. X squared plus y squared equals dx 25, okay? And using your sum and products rule, you're going to notice that the derivative of x squared is just 2x, and the derivative of y squared is 2y dy dx, okay? And that's actually, and there's actually a dx over dx here, but that just cancels out, okay? That's basic fractions. And over here you have 0, okay? Next, what you're going to do is you're going to do the exact same thing as we did up here. You're going to get the dx by itself, okay? So you're going to do 2y, or 2y times dy over dx equals negative 2x. So dy dx just equals negative x over y. Alright, right there. Straightforward, okay? And now we're being asked to find the slope at 3 over 4, right? Because we're asked to find slope at 3, negative 4, okay? So what we're going to do is we're just going to evaluate. So dy dx at 3, negative 4. What you do is you plug in, right? So now you have negative 3 over negative 4, and that's just equal to 3/4. So the slope of the circle at this point, 3, negative 4, is 3/4. Okay? Now the implicit solution is actually much easier because, as you can see, we didn't have to go through complex differentiation. But at the same time, it's a much more universal solution. Why? Because with this function, if you were to do this, then you can find the slope at any point on the circumference of the circle. Whereas if you were to derive y2, then you can only find the slope of the circle for any point that is below the x-axis. Okay? Now, let's move on and do another example, right? This is example number 3. Example number 3, okay? And it asks us to show that the slope of dy dx is defined at every point, right? Defined at every point of the graph 2y equals x squared plus sine y, okay? So first we need to know what dy dx is, and we're going to, once again, solve by implicit differentiation. So now we're going to do d dx of 2y equals d dx of x squared plus sine y, okay? And of course this becomes, so this side comes out to be 2x plus cosine of y dy dx, okay? And on the other side, you're going to come out with 2 dy dx, right? And so 2 dy dx equals 2x plus cosine y dy dx. And so what you're going to do right now is you have to get dy dx to one side. So you're going to subtract. So 2 dy dx minus cosine y dy dx, right, equals 2x. So you factor out a dy dx, and then you end up with 2 minus cosine y, okay, equals 2x. Now it's very straightforward. You divide by 2 minus cosine y on both sides. So now you get 2x divided by 2 minus cosine y, okay? Now you have dy dx, and so the formula for dy dx is defined at every point x, y, except for those points at which cosine y equals 2. Now since cosine of y cannot be greater than 1, this never happens. Which is why we have to which is why the original problem holds that the slope dy dx is defined at every point on the graph 2y equals x squared plus sine y.